Hi guys, in this video we're going to introduce another technique of integration. In this section we'll look at functions that happen to be rational expressions, that's a polynomial over another polynomial, where the degree of the numerator is less than the degree of the denominator, and we happen to be able to factor out the denominator. So as an example, let's take a look at the following integral, x plus 5 over x squared plus x minus 2 dx. So your first thought might be to try to use substitution. If we let u equal x squared plus x minus 2, why would I choose that? I choose that because this guy is a composition. But then we see that du is 2x plus 1 dx, and we're in trouble. We're not getting rid of all of the x stuff. So u substitution won't work. However, let's take a look at this rational expression inside. Let's note that x plus 5 over x squared plus x minus 2 is the same thing as x plus 5 over x plus 2 times x minus 1. So I claim that we can find constants a and b such that this rational expression is equal to these guys. So think about this for a second. Typically in a lot of math classes you have something that looks like this and you need to combine these guys into one expression, simplify it so that you might be able to solve some sort of equation. So now I'd like to go backwards and try to find an a and a b such that these guys are equal. So pause the video for a second and don't worry about actually finding a and b, but pause the video and try to explain to yourself why that would be good in terms of trying to integrate this. Right? Well, hopefully you said to yourself, well, if I can find an a and a b where these guys are just numbers, then I can integrate this guy using u substitution. I can integrate this guy using u substitution. Therefore, I'd be able to integrate this guy. So our goal is to find an a and a b to make this work. Well, the first question is, will such an a and b actually exist? I don't want to go through the work and actually come up with no solution for a and b. Well, it turns out that there's an algebraic proof which is a bit beyond the scope of this course, which will convince us that we can actually find an a and a b. So I'm telling you ahead of time, I know I can find an a and a b. The question then becomes, how do we do this? Well, for these guys to be equal, all I need to do is create a least common denominator, in this case x plus 2 times x minus 1. Once I have the same denominators, I can set the numerators equal to each other. In other words, this is the same thing as a times x minus 1 over x plus 2 times x minus 1 plus b over x minus 1 times x plus 2 over x plus 2. In other words, the least common denominator is x plus 2 times x minus 1, and I just gave each of these guys what they needed. Well, again, my goal is to find the a and the b. For this to be true, the numerators would also have to equal each other. So let me set x plus 5 equal to a times x minus 1 plus b times x plus 2. So I want this to be true, this should be true for any x that I plug in. Pause the video for a second and try to think of an x that you might be able to plug into this guy to make it easy to solve for b. Well, hopefully you said x equals 1, because if x equals 1, this becomes 6. X plus 1 plus 5 is 6 is equal to 0 plus b times 1 plus 2, or 3. So this tells me that b is equal to 2. So I'm going to erase this up here and rewrite this as a 2. Hopefully you see the game that we're going to play. I'm going to set x equal to minus 2 to solve for my a value, because then I have that minus 2 plus 5, or 3, is equal to a times minus 2 minus 1, or minus 3, plus, once again, stick the minus 2 in there and I get 0. So I guess that a is equal to minus 1. So I've now come up with a sum of two rational expressions that equals the original rational expression, and this is something I know how to integrate. So let's take a look at how that would work. So this guy here is just the same thing as minus 1 over x plus 2 over x minus 1 dx. And I can just do this term by term. We have minus 1 over x plus 2 dx plus the integral of 2 over x minus 1 dx. So let me just make a little dividing line there. Here I'll let u equal x plus 2 so that du is just dx. And it looks like this is the same thing as the integral of minus 1 over u. My du is just dx. And let me add to that. See, u equals x minus 1 here. Du is just dx. The derivative of x minus 1 is just 1. So this will be plus 2 over u. The u is on the bottom because u is x minus 1 du. Then this is just a basic integration formula. This is minus 1 times ln of the absolute value of u plus 2 times ln of the absolute value of u plus c. And we have to be a little bit careful here. This u is not the same as this u. So let me put these guys back in. So this u was x plus 2. And this second quote-unquote u is going to be x minus 1. And this is this will be the family of antiderivatives related to this guy. So this is case 1. So let me articulate what this is looking like. Case 1 is where I happen to have a non-repeated linear factors. In this case, I have x plus 2, which is a linear factor, and x minus 1 is a linear factor, and they're different, so they're not repeated. In this case, all I need to do, and let me just write the specific example, is have each of these factors under a different letter, and then solve for those solve for the a and the b. You'll then be able to solve the integral by using u substitution. Again, why does such an a and b exist? That's from that theorem, which is beyond the scope of this course. But you'll always be able to solve for those guys. All right, so that's case 1. We have 3 separate cases that we're going to be looking at today. The second one being when we have a repeated linear factor. So let's say I have 1 over x minus 1 squared times x plus 2 dx. So by that theorem, once again, it turns out that we can find constants a, b, and c, which make these guys equal to each other. So what am I doing? For each repeated term here, I'm adding another factor. So if this were a cube, I'd have to have a over x minus 1 plus b over x minus 2 squared plus c over x minus 2 cubed plus d over x plus 2. But here I only go up to the second power. Again, I want to be clear about this. Why that works, why we know we're going to be able to find an a, b, and c is due to that theorem. And without really diving into the theorem, we can't understand why exactly this is going to work for us. I'm telling you that it will because we're not going to actually prove the theorem. Before we actually find the a, b, and c, once again, please pause the video and tell yourself how the heck you're going to integrate this once you find an a, b, and c. Right, hopefully you said, oh, this first one you could just do u substitution. The second one you could just do u substitution. This third one you could just do u substitution. So our goal now is to find a, b, and c. And to do that, once again, we'll play the same game we played before. We'll find the least common denominator and then set the numerators equal. So I invite you to try that step before I go through it. So if I were you, I would pause the video for just a couple minutes and see if you can find an equation that we could then use to solve for a, b, and c. Right, so hopefully you had 1 over x minus 1 squared times x plus 2 is equal to, well, what is the least common denominator? The least common denominator is this guy. It's x minus 1 squared times x plus 2. So this term here, already has an x minus 1, so I guess I need another x minus 1 and I need an x plus 2. So x minus 1 times x plus 2. And I multiply the bottom by x minus 1 over x plus 2 as well. So what does the b term need? Well, the b term has the x minus 1 squared on bottom, so all we need is an x plus 2. So we'll multiply that by x plus 2. And the c has an x plus 2, but it's missing an x minus 1 squared. So let's give it an x minus 1 squared. And then once again, what we'll do is we'll just set the numerators equal to each other. So I have 1 equals a times x minus 1 times x plus 2 plus b times x plus 2 plus c times x minus 1 squared. All I did is I set this numerator equal to this guy. And we want that to be true for all x's. So what would be some good values for x? Well, how about x equals 1? If x equals 1, this will go away, and that'll go away, and I'll be left with this guy. So if x equals 1, that zaps out, and we're left with 1 on the left-hand side equals b times 1 plus 2, which is 3. So b is equal to 1/3. So first off, I like to start filling things in here so I see what I have. And let me also put it in here. So what would be another good x value? How about x equals minus 2? That'll zap out, and we'll be left with this guy. So x equals minus 2. So we have 1 is equal to 0 plus c times minus 2 minus 1, or minus 3 squared, which is 9. So 1 is equal to 9c. So c is equal to 1/9. So again, let's put this up here. And let me put it down here. So now I need to find a. Well, I can't plug a negative 2 in because that'll zap out. I can't plug a 1 in because that'll zap out. But again, this has to be true for every x. So at this point, I just plug in an x, which makes my life easy. So a small number such as x equals 0. So plugging in x equals 0, we get 1 is equal to a times 0 minus 1 times 0 plus 2 plus 1/3 times 2. 0 plus 2 is 2, plus 1/9 times 0 minus 1 squared. 0 minus 1 squared is just 1. So we need to solve this for a. Let me get a least common denominator. It looks like everybody is going to have to be over a 9. So this is the same thing as 9 over 9 is equal to minus, let me do this in a couple of steps, minus 2a plus 2/3. 2/3 is the same thing as 6 over 9, multiplying top and bottom by 3, plus 1 over 9. So 6 plus 1 is 7. We have 7/9 here. We have 9/9 here. So I guess I just have 2/9 is equal to minus 2a. And then I can multiply both sides by negative 1/2. And I'm left with a equals minus 1/9. This guy is minus 1/9 up here. All right, so all of that work is what I would call pre-calculus work. We're now ready to actually integrate this thing. And what we're going to do is we're going to do it term by term. In other words, the integral of this dx is going to be the integral of this dx. So let me look at each of these guys separately, since this is a complicated enough problem. So for the first one, let me pull out the minus 1/9. So that's one integral that I'm going to want to look at. Let me pull out the 1/3 from this guy. Another integral I want to study. And then finally, let's take a look at this third guy. And that's the third integral. So here we can make a u substitution of u equals x minus 1. So that du is equal to dx. So this is the same thing as minus 1/9 the integral of 1 over u du, or minus 1/9 ln of the absolute value of u, which is just x minus 1. And I'll hold off on the plus c until the bitter end. And that's this guy. This guy, I'll let u equal x minus 1. Du is then dx. So this is the same thing as 1/3 of the integral of 1 over u squared. So thinking ahead to a reverse power rule, let me call that u to the minus 2 du. So this becomes u to the minus 1, u to the minus 1 over minus 1, or times minus 1. So we have minus 1/3 times 1 over u, which is x minus 1. And then finally, this guy looks just like this guy, so I guess we'll let u equal x plus 2. Du is dx. So that this is 1/9 the integral of 1 over u du, which is 1/9 ln of the absolute value of x plus 2. Again, ignoring the c's for now. But what I can do is I can now combine all these guys to get minus 1/9 ln of the absolute value of x minus 1, that's this first piece, plus minus 1/3 over 1 over x minus 1, that's the second piece, plus 1/9 ln of the absolute value of x plus 2, plus, that was the third piece, plus c. Phew! So that's a lot of work, and let's talk about what this case is. So this case is where we have a repeated linear factor. So repeated linear factor. And the thing to remember, and let me do this, let me show this by example. The thing to remember is that for each term that gets repeated, we need a separate variable that we're solving for. So that, in other words, we have a over x minus 1 plus b over x minus 1 squared plus c over x plus 2. So that's the second type that we might encounter. And again, what it does is it converts something into something that we can integrate into something that we actually can integrate. So there's one more case that we're going to study. Let's check it out. So the example I have in mind is the integral of 1 over x squared plus 1 times x minus 2 dx. And what this guy has is a non-repeated quadratic or irreducible quadratic factor on the bottom. In other words, I can't factor x squared plus 1 into x plus something times x plus something else. So that theorem, that once again we're not going to prove, tells us that if we add an ax plus b, in other words, we have a letter times x plus some other letter for that quadratic term, and then an individual letter or variable for the non-quadratic term or terms that are left, that we can actually solve for an A, B, and C to make this work. All right, so let's play the same game that we've been playing. It looks like, let's see. So this integral isn't equal to this. I guess I'd say that this integral is equal to this integral, and we want to try to find the A, B, and C first. So we have 1 over x squared plus 1 times x minus 2 on the left. That's going to be equal to ax plus b over x squared plus 1 times x minus 2. So where am I getting the x minus 2? This is the missing factor, so I'm trying to find using the least common denominator, plus c over x minus 2 times what it's missing. So it's missing x squared plus 1 over x squared plus 1. So once again, let's set tops equal to each other. So we get 1 is equal to ax plus b times x minus 2 plus c times x squared plus 1. And once again, let's try to think of values of x that'll be helpful here. Looks like x equals 2 is going to be helpful, because that'll zap this piece out. So if x is 2, we have that 1 is equal to c times 2 squared, which is 4, plus 1, which is 5, or 5c. So this tells us that c is equal to 1/5. When we plug this in, all right, so what else might be a good one? Well, if I let x equal 0, that'll zap that guy out. So let me do that. X equals 0, so we get 1 is equal to, so that's 0. That's b times minus 2. That's that piece. Plus 1/5 times 0 squared plus 1, which is just 1. So I'm left with 1/5. Subtracting the 1/5 from both sides, I get 4/5 is equal to minus 2b. No reason that I put this out front. It's just customary to put numbers before letters. And then I can multiply both sides by minus 1/2. And it looks like b is equal to minus 2/5. So b is equal to minus 2/5. Let me actually put these guys up here. So 1/5 minus 2/5. And then finally, we need to solve for the a value. So again, you can actually plug in any number you want. So I'm going to plug in an easy number. I'm going to plug in x equals 1. So when I say easy, I'm just thinking of a small number. So let's see. This is a minus 2/5. 1 minus 2 is minus 1. 1 squared is 1. 1 plus 1 is 2. 2 times 1/5 is 2/5. So I'm in the world of fifths, so let me call this 5/5. I'm going to subtract 2/5 from both sides, and I get 3/5. Now let me multiply through by -1 to get negative a plus 2/5. Subtracting 2/5 from both sides, 3/5 minus 2/5 is 1/5. That's equal to minus a. So I guess a is equal to minus 1/5. All right, so let me put this up here. Again, at this point, I claim that you can actually integrate this thing. Give yourself a minute, see if you could figure out how to integrate that, and then press play again. All right, this is what I'm going to do. I'm going to think of this as the integral of minus 1/5 x over x squared plus 1 dx plus the integral of minus 2/5 over x squared plus 1 dx plus the integral of 1/5 over x minus 2 dx. So notice I just broke up the numerator there. And let me just clean this up a little bit before we dive into the integration and I explain exactly how these guys can be integrated. So I'm just going to pull out constants when appropriate. So the minus 1/5 can be pulled out. The minus 2/5 can be pulled out. The 1/5 can be pulled out. And now let's study this to make sure we can actually integrate it. This is just a u substitution. This guy is just arctangent. That's a basic formula. And this guy is also a u substitution. So let me take care of each of the pieces. So we have minus 1/5 integral of x over x squared plus 1 dx. So I'm going to let u equal x squared plus 1. du is then 2x dx. I can divide both sides by 2, aka multiply both sides by a half. So let's see, in u world, let's see, x dx is equal to 1/2 du. And this guy is just 1 over u. So this is the same thing as minus 1/10 ln of the absolute value of u. I'll add the c's in at the end. Or minus 1/10 ln of the absolute value of x squared plus 1. Truth be told, you don't need the absolute value there because x squared plus 1 is at least 1. In other words, it's always positive, so absolute value doesn't do anything. Okay, so I think what I'm going to do it a little differently than before. I've got a lot of information on the board, so let me start filling things in here. We have minus 1/10 ln the absolute value of x squared plus 1. And let me take care of the second guy. Well, actually, the second guy is already taken care of, as I said. That is just a basic formula. So minus 2/5 arc tan of x. So that's that guy. So let's take care of this guy now. So we have 1/5 the integral of 1 over x minus 2 dx. I'm going to let u equal x minus 2. du is then dx. So this is the same thing as 1/5, the integral of 1 over u, du, which is our good friend natural log, the absolute value of u, or 1/5 ln the absolute value of x minus 2. So let me add that in here, plus 1/5 ln of the absolute value of x minus 2, and finally, I will add the c back in. So the third case, again, is if we have a non-repeated irreducible quadratic. Let me be clear about that. Or let me say, yeah, irreducible quadratic. And the example that I had was 1 over x squared plus 1 times x minus 2. And again, by that theorem, if we have an ax plus b over our quadratic term, and we have a c over the other term, then by that theorem, we're going to be able to actually solve for those ab's and c's. So that's it. That is the method of partial fractions. And now the next thing to do is just practice problems with that. All right, thanks so much. Bye-bye.